Hello, everyone. Here we are for episode number 4 of this 68,000 assembly course based on the book of Fabio Ciucci, which I thank for letting me stream his book, basically, or doing this series on his book. I also would like to thank um, all the members of Phase 101 and all those that join Phase 101 or follow Phase 101, all those that are in Commodore Dev, in the Facebook group Commodore Dev. I also like to say thanks to retro programmers inside. No, I don't know if Manuel is here today, but yeah. Also, I'd like to thank um, all the people, which is incredible. I did not expect this. Since we launched the video of the first episode, the amount of subscribers to YouTube and to Twitch has increased, and I'd like to thank you because this means, hi Emanuele, this means that you know this is not work that is not, it's an appreciation for this work. um Behind me there are other people that help me, and I need to thank them too. One of them is Crane. um but there are others, and there are also others that inspire me, like Shalan and like OSK, old school coder. So yeah, it's amazing. I started this journey not thinking, to be honest, I didn't think it will go this way. I just wanted to share what I've been learning um, with um, with the rest of the community on the Amiga. So it's quite nice to see others basically supporting or enthusiastic about this. The I have a piece of paper. Where did I put it? Here it is. So I always say this, but um, I need to say it because I need your support. Although I just said that you're supporting me, please subscribe to my Twitch. Please subscribe to YouTube. Follow us on Twitter and Instagram. Join us on Discord or Facebook group, and like our Facebook page. If you have any questions or in relation to this series, please do not hesitate to message me. You have all these options how you can reach us, so it's not an issue. So we need to continue where we left. For those that weren't here last episode, I'm just going to show the last example that we did from chapter 2, which is we are talking about addressing modes of the 68,000. To be fair, the first example was long. The next examples are very long. There are about 10 or 11 of them. They are very interesting. I mean, it's amazing how from one example he managed to show addressing modes the way he did. Because many times you find it in books and you see addressing mode explained, but by words, not by example. And the way he showed it is very cool. So I'm just going to go back to the Amiga. I'm going to, I believe, because I load them already today. Okay, let's do this and accept accept the one that we did last. Um, RamJam, sorgenti. So this was the example that we did last time, just to show you. Hit it. Um, it's the same example, but we had a counter, okay, to count how many times we press, for how long we press the right mouse button. So A J, okay, And now if I press the right mouse button, okay, there's a counter being incremented, and that counter, when we exit, we know what value it will have. Okay, so the counter, maybe not, it's in the memory, sorry. I needed to do contatore, so D or M, whichever, D, because we have a defined constant block. So as you can see, the BO55 is what, because it was a word, is what's being stored. So basically that's how many times or how many frames passed till we release the mouse, the right mouse button. Okay, so now let's continue with the actual book. We arrived here with the 2A. You have seen how powerful the .L, .W, or .B are in in when you add them to the instruction, basically like move you to do .L or .W or .B. So keep that in mind, because thanks Skynet060 for joining, following the stream. For some reason, I was not alerted, Skynet, about your about you joining, but I saw the message. So he's going to continue talking a bit about binary, okay, and he's going to give an example, and this is just to make you aware, because if you are used to the 8-bit computers, you will not be thinking, um, eh, even though you do binary and you know it, you will not be thinking the same like if you have a 16-bit machine. And the reason why I'm saying this is, if you have a 16-bit number, okay, it is, you have from 0 to 15, okay, so remember 9 and then it's A, B, so but he's showing it from 0 to 15 basically. Here, without sorry, here, without you knowing, okay, in this example, okay, this one, without you knowing, there's another 4 zeros, because it's binary, it has to be, it's a word. So just to be not be confused, okay, about numbers, um, because you might see it and you say, ah, okay, it's 110, but it's actually 0110 for the assembler. Okay, so this is why he's showing that there is from 0 to 15. Basically, remember, we always start from 0. Now, do you see that we are testing for, we say bit 6, but actually, okay, it is bit, if you had to count from 1, like the normal system, like the decimal system, that is bit 7. However, remember, we always need to think about binary, and we start from in computer STEM, and we start from 0. So we are testing bit 7, which is 0 1. Okay, bit 7 is 0 1 0 0 0 0 0 0. Okay, hence it is hex 40. Okay, if we had to convert that um, into hexadecimal, but it makes more sense um, to talk in binary in this case, because we are doing a bit test. Okay, and remember, all custom chip registers are 16-bit wide. Okay, so the 7th bit, okay, remember we start at 0, so 1 byte is 8 bits, so the 7th bit is called the most significant bit. Okay, Please note also that when testing for the mouse, we get at 0. Okay, so before when I was doing a bit test, okay, we get at 0 when the mouse button is pressed, else it is always a 1. Okay, so when we are testing for a 0, not for a 1. Know that the bit test, okay, only works, and this I will show you in a minute, only works on byte, okay, dot byte or dot long. The bit test, the instruction bit test doesn't work on dot w. It doesn't support it. And you will see in a minute, it doesn't make sense to do dot word in bit test, okay? So it's logical in a way. So dot l only, you can only use dot l with a data register as destination actually. So in reality, it's always .b, but if you're using a data register, you know, from one of the D0s to D7, then you can use .l. Now, just to, this is the PDF that I had shared previously with you guys about the 68,000. If you don't have it or you don't lost the link, etc., go to our Discord channel, and in the Discord, um, in our Discord group, there's a channel dedicated to this stream, and you should find all the links there. And it's where we actually discuss this series. So you can see that bit test, first of all, attributes, there is only byte, okay, and long word. So there is no word, okay. And bit test, if it's a data register, okay, to an address, of course you are comparing to a doing bit test to an address register, okay, EA address register, effective address. Then you can use a data register and do a test with using the 0, for example, or the 1. Else, else it's always, if you're using the immediate mode, then it's always from 0 to 7, okay, that you can test. There's no more bits in a byte, of course. Okay. So this is something that most of you know, but I'm going to cover it because it's in the book. A word is 15 bits, and the range of bits is from 0 to 15, which we already covered. And the range, the number, is from 0 to 65535, okay? Now, if you're using a long word, which is a 32-bit, okay, the range is from 0 to 31, okay? And the maximum number, as it is written here, is 4 million whatever 29496722299, okay. So that's basically it in terms of ranges. So he, in a way, he already covered one addressing mode, which is the absolute addressing mode, okay. But now we are going to talk really about addressing mode and clearly about addressing mode. So we have seen that doing CLR, okay, CLR.W 100, okay, we are actually clearing memory locations, okay, 100 and 101, okay. When I say the 100 and 101, they are in hex. Remember, this number is hex here. Also, if we do move byte, okay, 100 to 200, okay, he's talking here 100 to 200, okay, we are actually moving the content of what's in 100 to address 200, okay. We can also indicate the same with labels. So instead of having 100 and 200, we could have said label 1 and label 2. You can So this was always absolute addressing, but he enhanced it a bit by using labels. Okay, but now what if instead of our own instead of an address, the source, it will be a number that we give. Okay, and that is immediate mode. Okay, which you do it with the which you say that it's an immediate mode by adding a hash, okay, at the front of it. So if we say we want to move in label 2, just like that, okay, if we say we want to move the number, the actual number, 50,000, okay, hex, okay, we do move L hash, because it's immediate mode, we are specifying the number, and 50,000, okay, dollar 50,000, that is hex, and then the label, which is label 2, as I said before. So this means move the actual number, move the number. I know I'm repeating this, but some people get confused by the immediate mode and absolute mode. Okay, so this is why I'm repeating. If you see a hash at the front, you are in immediate mode. You can also use an immediate mode, the hash, I mean, in front of a label. Okay, so move.long hash, I don't know, I'm going to use phase 101. That's the word that always is in my mind, comma, label 2. Okay, just to um, give an example. So here, okay, he's going to start giving examples. Okay, look at these two instructions. Okay, in the first one, we are moving the 4 bytes that start at address 50,000 to the 4 bytes, okay, that are at 60,000. Okay, here, okay, we are moving immediately 50,000. So it's not, so 50,000 here, because we do not know what is the contents of 50,000 here. It could have been 1 2 3 4. Okay, so 60,000 will have 1, 60,001 will have 2, and it will continue like that. Okay, so whatever value there was in 50,000, it will be moved to 60,000, 50,001, etc. While here, we are actually specifying that in 60,000, okay, there will be, okay, the 50, um, the 50,000 that we specified, and that is written. And remember, there's a 00 because this is hex, and because it's a long word, okay, so we have 1 2, okay, there's a 0 in front of the 5, and then there's another 00, okay, so 60,000 will get 0, 60,001 will get 05, 60,002 will get 0, and 60,003 will get 0. Okay, maybe I should draw this so that you visualize it for those that find it difficult. So when we move, if we move 50,000, okay, first of all, that in hex, or for computer terms, that is written in memory 0005, okay, and 0000, okay. Did I say 50,000 or 5,000? That's 5,000. Sorry. Um, yeah, let's assume it is 5,000 instead of 50,000. Okay, let's assume it is 5,000, not 50,000. So then, okay, 6,000. Okay, sorry, 60,000. Address 60,000 will get at 00. Uh, address 6001, okay, will get 05. Okay, so this is how it is basically. Okay, 6002 will get 00, and 6003 will get 0, 0. That's how they will be in memory, and it's quite important that you understand this. Okay. Um, so he continues by giving more examples, and the examples are very good in understanding. Many people confuse this term. Okay, so I cannot stress how lucky we are that in this book this is explained quite clear, and you will see it in the examples in a minute. Okay, so he's moving the label cane to gatto. Okay, so what he's saying is cane, which is down here, okay, has got in it 1, 2, 3, 4, 5, 6. Okay, and gatto has got 0. Okay, so basically we are moving, okay, what's in cane, address cane, okay, the 1, 2, 3, 4 to address gatto, same like we did before. Okay, so we move the contents of cane to gatto now, and he's saying dopo, okay, before and after. So he's saying what they will contain here, okay, after the move. Now imagine we had, and this is where it can be tricky. Okay, imagine we had, instead of move.long cane comma gatto, move hash. Okay, so immediate mode comma gatto. Okay, so what will happen is, if the address of gatto, okay, is 000345500, what actually will happen, we will not move the content of cane, but we will move the address of cane. So this is before and here is after. Okay, and you will see we have 34500. Okay, I think that makes it quite clear. I'm trying to show them both on the screen if I can. Oh yeah, it's going to be difficult, but you got the gist. Okay, so move long hash cane comma gatto to cane DCL. I mean, in cane we have the 1, 2, 3, 4, 5, 6. Okay, okay, let's continue. So we did that. Let's see if I missed something. Okay, so note also that the move here is an L, is a long word. Okay, but we could have specified okay, move W or more or move byte. Okay, in reality, okay, and I said it, but I didn't continue the sentence. I said it just to see if in reality, okay, listen to my English. I said we can use, okay, move.w hash cane to gatto, or move.byte, okay, hash cane to gatto. In reality we cannot. Okay, we really cannot. Why? Because we are moving an address. An address is always a long word, so you need to specify the long the you cannot use it, will give an assembler error. Okay, because we are trying to move to an address, and this is where many of us fail, including me. I did this error so many times. Okay, and I'm pretty sure that Crane has got my same view on this. Many times we try to use move.w or move.byte, and then we realize we cannot, because it is an address what we are dealing with. Okay, so you cannot have that. And you see the label, I put a note for myself here. The label is an address, and an address can be a word or a byte. It is always a long word, okay? But now that I know it, okay, I knew it from I knew it by experience now, basically, because I've read the book already. But um, and because I've been practicing some things myself. But yeah, it's a mistake, and I can tell you that you will still do it, even though you know it, you will still do it. So it's one of those culprits of the 68,000 that you're always caught up with. Okay, so let's look at example 2. Okay, I'm going to move. Yeah, I need to move this and have the Amiga in place. Okay. I will need the other book now to be. Okay. So so this is to be. As you see, it is very. It's a very easy example. Okay, he's not. Although there's lots of text. The code is not long. It's all this. It's with not even 6 lines, I think, with removing all this skip lines. Okay, so what we need to do here, and I'm following the book as much as possible because he recommends some steps that we should do. I'm going to bring it more closer to me, um, so that I can see better what he's talking about. Okay, so as you see, he's doing an immediate, okay, cane to gatto. Okay, so basically we are moving the address, okay, of cane, okay, to gatto, and this is very easy to find out. Okay, so if I assemble this, okay, and execute it, okay, and then undo the uh, gatto. I do not know how to write Italian, but that is understood. You can see, I mean, forget what is here, okay? So forget the assembly of it. But in the memory, okay, where it is, okay, we have the address 40189644. So if we go up, okay, you see here is where we have the 123456 stored at the address of cane, okay? And the address of cane is 40189644. And what do we have stored after the 123456? For gatto is 40189644, okay? So we copied, it's quite, I think the example is quite clear. We copied the address of cane, okay, to where the 123456 is, okay, the to um, to our gatto. Okay, that's basically a simple example. I'm going to go to read more in relation to his notes now, because as you know, Fabio doesn't know how to do an example without writing lots of notes, which is good for us, but I'm just making fun of it, and thank him at the same time. So with this source, you will realize that when the we assemble the address of label, the address of the label is used. Okay, so basically you can see at the top here that move long hash cane, we have the hash. Okay, once we execute it, okay, once we assembled it with A and D, we could have done also, we could have done D initio, okay, so we see this source properly. Why did I write initio wrong? D. Oh, of course, I need to assemble it to have it. D initio. And still. Something is not right in the way I'm executing the commands. Okay, so if we assemble it, and then we assembled it, but I don't think we need, if we do that, yeah, that's better. We are in debug mode. We can see, okay, come on. Yeah, because we only have one instructions and I told you to execute all. So we can see right now that we cannot see it there actually. We can see at the bottom, okay, what we are doing, okay. You can see the move long, okay, the 40189644, okay, because we remediate, so the address of label. So look how the assembler transformed the instruction to the address of Kane, which is 40189648. This is basically how all that was transformed. So keep that in mind. That is what actually happens, transparent to you on the on the assembler, okay, from the assembler side. Let's see, guys, if you write any messages right now, I will get back to them later on because I cannot really see them. So just bear with me. So that's one thing that he mentions. Let's see if he mentions something else in the exercise. So further down, okay, so let me come here again. Further down in the source, of course I need to go in edit mode. Okay, here he has some more examples. Okay, note, okay, we are moving, okay, what's in address 10 to address 200. Now address 10 is address 16, okay, so when because this is hex, it is address 16, okay. But here, okay, we are moving 16 to address 200. It's not the same, okay. One, we are moving the contents, and here we are moving the actual value of 16. However, further down below, we are moving, so these three are all the same, okay. We are moving immediate 16, so decimal 16 to 200, and we are moving the binary 16 also to 200. So all three, okay, all three is means we are moving 16 to address 200, and that is to explain the difference. Except for the first one, which is different, the others are all the same. The only difference between them, the last three, is that we are using hex, decimal, or binary. Now, this is something that, for those that come from the 8-bit, let's say, programming on 8-bit machines finds it abstract. I remember myself how abstract it was to me to think about this. Okay, please note that everything you run on the Amiga, okay, it is run in a different memory location each time. It doesn't mean that the next time that we run it, it's going to be at the same memory address. Okay, the OS relocates the code where it wants and how it wants because of its multitasking capabilities. Okay, so okay, we are not programming the hardware yet directly. Okay, so really absolute addressing doesn't really work on the Amiga. It's always relative. Okay, except when you are using programming the custom registers, those are fixed in a way. But even that, we use a mode in the 68,000, which is the relative one, which is the PC, which the book doesn't cover actually in this chapter, but we will I will mention it a bit because it's handy to have it, to know it. That's one concept, okay, that you need to keep in mind, that the next time that you run the code, it won't be in the same memory location. Although I have to say, if I run it right now again, because I'm using the assembler and I'm using the memory allocated for the assembler, um, it probably will execute in the bubble of the assembly. It will execute in the same memory. But if I was doing this through Workbench, it will not, or through CLI, it will not. I can tell you that. It's he mentions, okay, further down in the code, okay, somewhere down here. He mentions somewhere down here, just to tell you where I am, so I'm at the end of it, that we should not use fixed addresses. I already mentioned that. If we use fixed addresses on the Amiga, okay, you expect a guru, okay? Now, of course, the custom chips is one example. The custom registers is one example where there is um, fixed addressing in a way, but also in a way is kickstart is a fixed address. However, the routines can change. Um, he also continues saying, Fabio continues saying that if you auto boot, that means you bypass the OS completely. So what he's saying is, if you have one of these games that you are not able to read it with DOS, okay, or a demo that you're not able to read it with DOS, that means because it has its own bootloader, its own things, okay. So most of the time in those instances you can maybe use fixed addresses because you are referring to your own code, and your own code you can say I want it to load in this memory, in this particular memory location or something like that. By auto booting it is meant, okay, when you do not see the contents of the disk, as I explained, because the game will have its own bootloader and won't use anything related to the OS. You will have seen demos games, so I'm basically translating what he said, and that cannot be read by the Amiga DOS. These normally have their own bootloader, as I said. Let's be honest here, we are far from creating our own bootloader. First, we need to manage to get something on the screen. So right now we are understanding the 68,000 or trying to understand, but we are far away from that because we even don't even have anything on the screen yet, which will come. It's in the next chapter, and the next chapter is very very nice. Is something that everybody talks about. Probably many people do not know what the heck it is. They mention copper, but what copper really is, few people know. Only developers know. Let's say that. Okay, so now I jump back. I put the book back on the screen, and we continue from where we left in the book, and we are here. So the 68,000 has data registers, D0 to D7, address registers, A0 to A7. Okay. A7, I know I've said this in the past, but I'm just going to repeat it because it's good to hear it. A7, and also he repeats it. These things are, some of these things are repeated in the beginning, first two chapters. He repeats a lot because he needs to makes us aware of certain things. Okay, so A7 is used for something else also sometimes, but right now think of it like this: it's that it is just a stack. Okay, data registers can be, okay, so D0 to D7, okay, can be dot byte, dot word, or dot long. Address registers can be .w or .l. Okay, so I'm basically mm, translating somewhere here in the code. Okay, address registers has also special instructions that they work only on memory addresses, of course, because we are address registers. It's the only way you can do is work with addresses. One of them is LEA, and he mentions LEA here. Okay, which means load effective address. That is as is the real name in 68,000. However, Fabio calls it load entire address, which actually it does make sense, and you can think of it like this because load entire address means the full address. Okay, not part of it, not dot word or dot byte. It's the full address, the full 32-bit address. Okay, in fact, LEA, okay, the instruction LEA, okay, which you see down here, okay, does not take, okay, dot W or dot byte. It always works on a long, so you do not specify it, okay? So it's just LEA. You are just working on a long address, of course, because it's an address. As before, remember I told you it cannot take, you cannot do uh, move.word or move.byte immediate cane to gatto. You cannot because it's an address. It has to be a move long. Okay? And that's why I prefer using LEA instead of move.long when it comes to addresses because it makes more sense. Uh, Plus, it has some other advantage which I won't mention right now. So we are here. So the first one, okay, you can use it with data registers and address registers. So we can do a move.long, okay, instead of immediate 5000, we can do a data register, which is the 0 or the 1 to 80. So you're moving the contents of a register or an immediate address, okay, or an immediate value to 80. But um, the second one, okay, LEA 5000, we are actually moving, okay, and let me read to make sure that I'm not making a mistake. We are actually moving the address 5000 to 80. We could have specified label, okay, the text is coming up each time. So here where we have um, the same instruction, we could have written LEA label comma 0. Also, the second one, it will only work with address register. So after the comma, okay, there is 80. So always an address register. Okay. So if you had to use move-L, it's very easy to confuse that. So that's why I prefer using LEA um, in terms of this. Please note also that the examples in this chapter are quite long. As you can see, we only covered one, and we are just covering the second one, which we are coming to soon. Um, he could have included the text in the examples in the book because he has written another book with the examples, basically. Um, one feature of the LEA, okay, we were talking about LEA, is that it is faster than move.long, okay? So the instruction, the CPU, when you use LEA, knows immediately it's going to deal with address registers. So that's already a big part of the CPU that is already geared towards an address register. So that's why it is good to use LEA instead of move.long. Okay. Please note also that lower writing the in assembly, lowercase or uppercase, or the labels, it doesn't make difference. Most of the time, the assembler is configured to be case insensitive, okay, not case sensitive. So uppercase and lowercase are the same, and you have an option actually in the assembler where you can set this. But by default, it is like that. Okay. LEA is very powerful. Okay, so this is something that I'm these are my notes and are not written here. Okay, LEA is very powerful, is a very powerful instruction. LEA facilitates the writing of position independent code, okay, dynamic code or relocatable code, okay, in memory. It's a lot better than using move.long, okay. And I'm going to show it to, I'm going to write it to you just to understand. You can write, we will not cover this yet, but I'm just going to give you an idea, okay. So we can write LEA, okay. This is from my notes, not in the book, okay. Table, for example, okay, let's say we have a table of define constant bytes of table, okay, comma, and this is where it's powerful, PC, okay. So basically it uses the program counter to relocate that whatever it is in memory, okay, comma to 80, okay. So basically whatever table is in memory doesn't matter, and this is why the Amiga is able to do multitasking, one of the features, because the 68000 supports this mode um, of PC relocation. Basically the program counter can be anywhere, wherever it is, it moves, calculates it relative to the address of where table is, calculated relative, and it can shorten the instruction and can make it faster. But I will not, because I just wanted to see it for the first time. It is not something that is mentioned yet in the book, not even in chapter 2, okay. So just wanted to mention it to you to give you heads up on it, because it will come eventually. The text in white means that we do not need to read it, and here he's actually mentioning the uppercase and lowercase in the assembly and where to go and find it. But because we are using ASIM1, ASIM Pro, the instructions for finding it is different, so I can skip it. So notice the difference between these two, okay? So here we have more examples, okay? Notice the difference between these two. So we don't have an immediate now, okay? We have an absolute address of 5000, an absolute address of 5000. So here we are saying move what's in address 5000, 5001, 5002, 5003, the contents of, to 80. While here we're saying move, okay, the 5000 into 80. So one is the contents, okay, this is the contents of this address, and this is the actual address. It's nice of Fabio to give all these examples because he knows that when doing 68,000, this is where people fail. This is where those that try to learn 68,000 fail, and they get confused and they get disheartened and maybe stop trying. This is where people make errors, okay. Users like me or like you that try, where we make error, and I still make this error from time to time, um, because it's human. No, we are human after all. Okay, so now because of what I just said, we are going to do example number 2C. Okay, so let's move this out of the way again. What he's doing here, he has lots of examples. So it's quite an easy code, to be fair. He has lots of examples of showing what he's doing. Okay, so LEA cane, comma 80, move long immediate cane, comma 80, move long cane, comma 80, A2, sorry, and the other one is A1. And then once we store the addresses, we store the contents of these into the addresses, we move them to the memory location. Okay, but we can actually assemble this and run it. And first of all, you will see the results down here: A0, A1, and A2. Okay, so notice that A1, A0, and A1 have got the same. Why is that? So doing LEA cane, comma A0 and doing move.long immediate cane, comma A1, both of them mean the same thing. While move long cane, comma A2, okay, means move the contents, okay, of cane to A2. Okay, um, that's why A2 is different. Okay, so that's the first thing to notice. Okay, and if we had to do the gatto one, no, not fatto, gatto one, you will see those numbers also stored in memory. Okay, you will see the first two are the same: 4018, 971A, 4018, 971A. So remember, this is the first long word, and this is the second long word, which we had in A0 and A1. Then you will see the contents of that we had in um, in A2, okay, because they come from cane. Okay, so the contents of cane, we will see them in at label gatto03. Okay, so these two are gatto01, and this is gatto02, these two, and this line is gatto03. Okay, it's just because of the conversion um, of memory of this assembly of it. Also, it looks like that. So what else Fabio continue to say? So first of all, we assemble and run it in assembly and shows us the value. So we already did this. Notice that the first two instructions return are the same. Yeah, they produce the same thing. They both make 80 and A1 have the same value. LEA makes more sense though in this case. As I explained, LEA makes more sense. Let me switch you back to the so that you see what I'm talking about. Yeah, notice that every time we assemble something and we execute it and we return back to the assembler, it always shows us at the bottom the registers. Okay, so you saw them, I read them for you. At the bottom of the screen there were the registers at 0, A1, A2, okay, etc. Of course, if you he gives an explanation now, and I think I better do that too. Okay, so basically these are this line on top is D0 to D7, okay, the data registers. Here, okay, we have A0 to A7, and as I said, A7 is the stack pointer. You can see that our stack is somewhere here, okay, and then this is the stack pointer for supervisor mode, okay, so um, sorry, for user mode, okay, which um, sorry, supervisor SSP is supervisor mode, USP is user mode. So you notice that this and this are the same. Okay, it's just a way of representing it right now. And SR are the value in the status registers, and here is are the flags, and here is the program counter, okay, and VBR, okay, is where it's not vertical blank, okay. It's a special address where it has been of the 68,000, which I do not want to go into. It's related to interrupts, where it has been relocated. This happens at startup and where it is right now. I shouldn't be talking about this right now. It will confuse you. Just know the 0 to the 7, 80 to A7, and that this is supervisor mode, which you don't need to. This and this are the same, the user's stack pointer, and this is the status register as a number and as flags, okay? The rest, ignore for now, okay? Remember, the status register is 16-bit, so it's 16-bit registers, okay? And this bit is always 0, okay? So these lines here, okay, these are the status bits, okay. Some of these are not used, and one of them is always 0. It's forced by the 68,000 for some reason. I don't know if it's related to something that will be upgraded in future of the 68,000. That's why they did it like that. But yeah, maybe somebody who's an expert can tell me more about this. We are going to start another addressing mode now, okay? We're going to start address register indirect. This is a beautiful addressing mode of the 68,000. Trust me. I wish the 6502 had this more. I mean, actually it has it, the 6502, but with registers you cannot really do much. But this one is nice on the 68,000. So we do here, we actually let's do what he's saying here. If we do move.long 80 comma d0, we are moving, okay, what's in 80 to d0, okay. But if we do move long brackets in brackets 80 comma d0, okay, we are actually moving the contents of what's in address 80 to the 0, okay. So, and this is, although I'm saying this instruction is there's something similar on the 68,000, you will notice how this will expand, okay. So all the other instructions that I'm going to cover, so I covered indirect, immediate mode, and now we have address register indirect. Of all the addressing modes now, they follow a pattern related to this, okay. And this is the beauty of it. Ciao Davide, and grazie Alessio Carzi, for subscribing. Much appreciated. So what I was saying is, everything in the 68,000, and you actually, I can show you so you can understand. So just notice this 80 in the brackets, okay. So let me go on top of the page. I show you all the addressing modes of the 68,000, okay, and look at them. They start from this one, and then it's an enhancement each time of that instruction, okay, including the one with the PC, which we will not cover in this chapter, okay. And forget absolute addressing, we already did. Immediate addressing, or we already did. And of course DN and the EN is data registers, so immediate is here, absolute is here, and the rest are built on this, okay. There is no more instructions, addressing modes different than this, Okay, I mean, these are two addressing modes, these are two addressing modes, and these are two addressing modes. Okay. Like these are, well, absolute addressing, one is word, one is long, and this is immediate. Anyway, just to show you how he actually quite intelligently divided the instruction set, or not the instruction set, the addressing modes. So if we had, and now I need to show you again. So if we had, and I need to enable the pen. If we had clear dot byte bracket A2, and let's assume A2 has got in it the 5000 that we were mentioning before. Okay, we are indirectly clearing the contents of the 5000. Okay, so if in 5000 we had the decimal number or binary number 101, okay, which is 5 in decimal, okay, doing clear byte A2, okay, it means we will make that 0, okay. That is address register indirect. Of course, the clear.byte can be .w or dot or dot long, okay. Also, just to be clear, we are just clearing one memory location, but we can clear 4 bytes at a time if we want to. In Italian, just for the sake, for those that understand Italian, I'm just going to say that this is called uh, indiretto for some reason. Um, it makes more sense for me, address register indirect, but it's just one word, indiretto. Here, at least this is what he writes. Um, Whatever. So now we are passing to example number 2D. Okay. So back to 2D. So you notice that today I loaded all the examples in advance, so I do not waste time in in loading and unloading, etc. And if I need to discuss something, I can easily do it. Now, F. We are in 3. Okay, 2D. Okay, so this is the example of 2D. Okay, so here instead of cane gatto, he mentions kanguro, which is a kangaroo basically. Okay, so the example here, and I need to find my notes. I closed them by mistake, I think. Okay, so let's see what he's saying here. So first of all, I can follow this without looking at my notes and then read what he wrote, what he said, just to make sure that I do this faster probably. So we get the address of Kanguro, okay, the address here, and we put it into 80. So we get the contents of 80, which is the 1, 2, 3, and we move it to the 0, okay. Then we do the same thing, but move long Kanguro, comma D1. this moves the contents. Okay, so this is the same as this line. Basically, we move the contents of kanguro, okay, so the 1 2 3 into the 1. Okay, here we move 80. Okay, so what's in 80, which is the address of kanguro, into the d2. Okay, and then here we take the address of kanguro into d3. Okay, so we should see some common. uh, every time I'm clicking escape in the wrong window, and it causes me a mess. So assemble J, and if you notice, uh, so the first one, so did 0. I cannot go up here because I'm in this mode, but I can maybe bring the text to book. Let's see if you can see this properly. I can hide that, I can hide that, I can hide that. Yeah, because I need both of them together. Okay. So, and I hope I don't click on this window because this will vanish. So, we moved the address of Kanguro into 80. So, address, okay, is here. 80 has got the address of Kanguro. Okay. Then we move the contents of Kanguro into the 0. So we see the 1 2 3 here. Okay, then we move the move.long kanguro comma d1. So we move the 4 bytes uh, of at address kanguro to d1. So d1 has also 1 2 3. Okay, and then we move 80. Okay, so 80 into d2. So you can see that these two has got the same value. And then we move the address of kanguro into the 3. So 1 2 3 end up to be the same. Okay, that's what we did. Now let's see what else he mentions in his text that I need to be mentioning. So with this example, you can note the difference between direct and indirect addressing. Okay, so it's a perfect example for indirect addressing. Remember, registered direct is like A7 to D5. Okay, storing the stack pointer into D5. Okay, move.long A7 comma D5. We use the registers indirectly like that. So we are in this part. So here, what changes here from the first example? So here, what do I say? Actually, is it equivalent? Um, yeah. He's just explaining. So this is equivalent to this, basically. That's what he's saying. Okay. And this uh, and this is equivalent to this. Okay, that's all he's saying here in the note. So this is equivalent to this, and this is equivalent to this. That that is all that there is to know there. Nothing specific. So we did 2D. We will soon jump to 2E. So that's a good thing. So here, this is, yeah. So this is where it is interesting. Notice how he changed the example in chapter 1, the only example we had, and he rewrote it using address register indirect. Okay, now unless I told you, you wouldn't know what this is doing, and the reason why is you don't know 80 to where it points. um, you are you, this is the problem when you use 68,000 and use the registers. Most of the time you do not know what it is doing unless you documented it before. Okay, so this is one of the difficulties that I have on the stream that I do on a Friday in dissecting our sources. Many times I do not I need to really look deep to understand what we as phase 101 did with our code, because um, although the 68,000 has a lot of registers, it also makes it difficult if you don't say what the registers are actually being used for, or you need to find in the code what they are being used for. But it's the same example of what he uh, same example as we did in chapter 1. Yeah, that's what he's saying. Now we can see this in 2e. Okay, so uh, there you go. So look how nice the code is, how short it is, and how much faster this code is. Okay, first of all, here you can see that we are loading the custom registers into the address registers. Okay, so this is vhpos r, okay, into 80. This is color 0 into a1, and this is the mouse button, okay, left mouse button, or where to check for the mouse, in a2. Now because we are not using move long and do the test, we are using actual instructions dealing with registers. Okay, look how short and how much more faster this will execute compared to the example one. Okay, the example one that we had in chapter 1. If you have a look at it, and you will see the difference, how much faster this will execute. And I can tell you now that there is a way of making it even more faster by even loading the immediate, okay, into a data register, and then bit test the data register against a2. Okay, and like that you're just using pure 68,000 instructions, and because they are internal, they execute a lot faster. Okay, so that's why you need to see what the registers are being loaded with before you actually execute your routine. Okay, before in the book he was showing just this part, okay, just this. I mean, okay, it was longer, but just to make you aware, he was showing only this. But now with this powerful instruction, look how short the code is. So let's see what I have in my notes in relation to this example. So basically what I said already, it's address register indirect. He's using address register indirect to achieve this effect and having faster. This code is faster since you are using the CPU registers to move data between customer not customer, custom chip registers. Okay. After the execution of this example, notice the registers 80 and 82, they will contain the customer, I'm saying custom registers. Okay, so we can try to execute it. Okay, this is the same code that we had. Okay, and look, the custom register, not the custom register, now the chipset, not even chipset, the registers of the 68,000. My God, what's happening to me all of a sudden? Has got the values, okay, of what we just had. So 80, okay, which is DFF006. So 80, there you go. It has our VH-POS-R register. This is color 0 and this is the mouse button, okay? This is what it read from, what it moved from VPOS, VH-POS-R to color 0, okay? Am I right in saying that before I commit? Sorry, because actually the other registers, the data registers, I'm not using them. So yeah, ignore those. The only one that we are using no data register. So this is from the previous example. All you have to see is this. So sorry for confusing you, but with what I said before, but only these three, you can see that they are loaded. We are not using any data register. Okay, so the values are from previous execution. Oh, he actually mentions it. I forgot that he mentions it. He's mentioning how we can improve this part, bit test, okay, immediate 0, A2. And actually, what he does in the example, look, he moved quick 6 into the 0, okay? I will come to move quick in a minute, okay? So the bit that we're testing into the 0, and then he's doing a bit test, okay, using the 0, A2, okay? So I need to come to bit test. So bit test. Let's cover bit test because it's an interesting thing, okay? And I'm going to read it because so that you can, I mean, not read all, but you need to understand what happens. A bit in the destination operand is tested and the state of the specified bit is reflected in the condition of the Z bit in this status register. That it means, I assume, there, CCR. I don't know why they're calling it CCR there. Actually, that's something that I need to check. The destination is not modified, okay, by the bit test instruction. It is if a data register is the destination, okay, then the bit numbering is modulo 32, okay, allowing bit manipulation of all bits in a data register. If a memory location is the destination, so in our case, it is, I forgot what it was. It is an address register, no? In our case, it is an address register. Okay, so that's what he's talking about. If a memory location, where was I? If a memory location is the destination, a byte is read from that location. The bit operation performed. Bit 0 refers to, I missed something, I'm not making sense now. If a data register is the destination, then the bit numbering is modulo 32, okay, allowing bit manipulation of all bits in a data register. Yeah. If a memory location, so we are using a data register. If a memory location is the destination, okay, a byte is read from that location. The bit operation performed. Bit 0 refers to the least significant bit. The bit number for this operation may be specified either statically by an immediate value or dynamically by the contents of a data register. It shows that my mouth is getting dry. Okay, so that is how the bit test works, and why I read that is to make you aware the difference between using a data register to an address register, okay, testing against an address register, and an immediate data, which is our case because we changed, okay, we changed. So we are using the N now, okay, he's using D6, if I'm not mistaken. Where is it? Sorry, D0. Okay, now look at move Q. Move quick, sorry, not move Q. Move quick. This is the first sentence is what you need to understand. Move quick. Move the specified literal to a data register. So moves what we are specifying to the 0. The literal data is an 8-bit field. So whatever we move is actually an 8-bit. Okay. Not anything else. Okay. Within the move queue opcode. Okay. And specify assigned value in the range of -1 to 8 to 1 to 7. So that 8-bit, okay, is divided into plus or minus. Okay, so if we want to move -1, it's easier and better to use move quick. Okay, instead of doing sub 1 basically. But look what happens when the source operand is transferred. It is sign extended to 32 bits. Okay, so the sign is extended. Consequently, although only 8 bits are moved, the move Q instruction is a long word. Yes, this is always a long word. Okay, what we are moving when we are uh, using it. Okay, and going to my notes now. I believe I did this. Yeah. So I said we can also optimize it even more by replacing the immediate number immediate 6 with a data register. Okay. So here, please note that instead of move.long, he used moved quick. Okay. As I specified up here. Okay. He used moved quick. Into the 0. Move the specified literal to a data register. The literal data is an 8-bit field with the move quick opcode and specifies an assigned value in the range of -1 to 8 to +7. When the source operand, I think this I copy and pasted from that book. When the source operand is transferred, it is sign extended. Yes, I copied that, so it's the same sentence. I do not need to repeat it. So you understood what's happening there. And now he actually gives some example in the code. So look at this. This we can use move quick. I'm just going the first one here, move quick, immediate 100, 0. We can do that, okay, because it is less than 1 to 7. Okay, so it's it's fine to use it. But the next instruction, move long, immediate 130, we cannot use move quick instead of move long because it is above 1 to 7. So we need to specify that. However, in the next instruction, move quick -3, 0, we can use move quick because it is part, it is in the range of -128 and +127. So please note, it is very normal to use as much address registers or data registers. So he just emphasized what I just told you earlier. Um, Please note that it is very normal to use much address register or data registers that the routine might need. Okay, this is to make code faster, but at the same time it makes it less readable. Okay. Okay, so now looking at the code above, okay, this small routine, okay, looking at the code above, it is very difficult to know what the address and data registers are doing or working on, since we can tell with what they have been initialized. Okay, so basically he's a repeating of what I said earlier, that it's very difficult to know what's happening with with if you use only address. If somebody presents you code with the address register not knowing what they have been initialized to. Okay, however, this as stated makes the code faster but at the same time difficult to read. This addressing mode of indirect addressing is very powerful and is very common to manipulate memory using these type of addressing modes on the 68000. But also it is weak, it's a weak point since it is difficult to know what is happening. That's the issue um, of it basically. Okay, so this example, okay, above. So oh, this is 2F and we are not doing 2F. No, we are doing 2E. Yeah. So I think I'm going to call it um, a day for today. Thank you very much. Bye bye.